Hi everybody, apologies for the delay in the second part of this project on the function generator due to some family commitments over the last few weeks. But now let's have a look at part two. We're going to have a look at the output stage of the project first, and then we'll look at the build of the project and one or two little alterations that I made to the original design of the circuit. Right, well here we see the circuit I've put together for the output stage for this signal generator project. I'm using 4 operational amplifiers. At the end of the day I decided not to use the TL084 quad op amp, and instead I've gone for a NE5532 Texas Instrument operational amplifier. The NE5532 op amp is well suited for our project today. It has very low noise. Each package is a dual op amp, so we have 2 op amps in a single 8-pin DIL IC, so we're using 2 of them today. The IC itself is internally compensated for unity gain operation, which is quite good for our project, and it also has internal output short circuit protection, which is ideal again for the project we have in mind today. So let's have a look at the circuit I've put together. Right, well this operational amplifier normally works off a dual supply. So what I've done here, I've split the 12 volt supply to give us plus and minus 6 volts by putting a potential divider across the normal 12 volt supply in the rest of the circuitry, and tapping off at the center there to give us a floating ground for the operational amplifiers here. And then in relation to that, this line here will be negative and that line there will be positive by 6 volts. So we'll have a plus and minus 6 volt swing. Right, well either the square wave or the sine wave stroke triangular wave signals is fed into these operational amplifiers here. These are configured as non-inverting amplifiers, low gain ones, as you see from the configuration I've used. I'm simply using a 10k resistor and a 20k preset to set the gain of these amplifiers. And the reason behind that is I want to equalize the gain between both the square wave and the sine wave, so that the amplitude of the signal is identical when it goes into the remainder of the output stage. The amplification of these particular stages, the gain of these can simply be calculated by the formula. If we call the 20k resistor R1 and the 10k R2, the gain of the stage will be R1 divided by R2 plus 1, and that will equal, in our case, the 20k divided by 10k is 2 plus the 1, means we have a maximum gain of this particular stage of 3. We don't need a lot of gain, we just want to equalize the signal amplitude going into the remainder of the circuit. And by keeping the gain low, the circuit remains fairly stable. Now the signal from these amplifier stages here is simply switched through a switch which either selects the square wave or the sine wave signal and feeds that into a non-inverting buffer stage. So the op amp here is configured as a non-inverting buffer by connecting the negative input to the output. The output of that is then coupled to a 10k potentiometer, which will act as our gain control for this output stage, and the signal from the potentiometer is then fed into another non-inverting buffer stage, and this time the output is giving a 50 ohm output impedance by simply connecting 2 100 ohm resistors in parallel. So that's the output signal from our function generator. So let's build this circuit now on a breadboard together with the remainder of the function generator and just test the operation of this and make sure it's working correctly. Well, here you can see I've laid out the project now on a larger breadboard. So the top part of the breadboard there is the circuitry that we had previously. So here we have the function generator IC and its components there. That particular IC down there is the Schmidt trigger IC, and there we have the Arduino Nano. I've just clipped the display on the back of this breadboard here so we can see it, and we have two switches there positioned. This one here will switch between the triangular and sine wave, and the other switch there will switch from square wave to pulse mode. At the front of the breadboard I have the frequency control, and what I decided to do is put a smaller value potentiometer in series with it to give us some fine tune of the frequency. This potentiometer here will be used to alter the pulse option, and this part of the circuitry here is the output stage, which I just illustrated on the whiteboard. So here we have the two NE5532 ICs wired up. There's the two presets which will set the gain, and there's the simple switch which will switch either through the sine wave or the square wave to the final output stage. And there we have the potentiometer, which is simply setting the amplitude of the output signal, and I've just connected the oscilloscope to the output to monitor the output here. Now the other thing I've done on this layout today is, if you remember the power supply we fed with a little mains transformer module which plugs into the power point, and that supplied a 12 volt AC to the circuit, and then we simply rectified that, and then we used a 12 volt regulator and a 5 volt regulator to set the voltages. What I've done here is I'm replacing the supply voltage now using a 12 volt little 12 volt switch mode power supply, which you can buy quite cheaply off eBay. This is set to 12 volts output, and what I'm doing then is feeding that 12 volts output into the circuit, so I no longer need the 12 volts regulator, and I don't need the bridge rectifier, so those have now been taken out of circuit, and we're simply feeding 12 volt DC into the circuit, and then we're dropping it down to 5 volts for with the 5 volt regulator there, which feeds the Arduino and the logic IC there. So what we'll do next is we'll switch it on, and I'll just explain another thing I changed following on from the part 1 of the project. Right, so we now switch on, and we should then see the output signal there on the oscilloscope, and the display there displaying the frequency in hertz. So it's at 2011 hertz at the moment, which corresponds quite nicely to what the oscilloscope is saying, which is 2012. The output stage here, as I said, we can switch between the sine wave or the square wave with the simple switch there. So if I flick that switch, we go to square wave, switch it again, we go to sine wave, and I can alter the amplitude of the signal with the potentiometer there. Right, I'm now going to check the output signal levels for this output stage. What we'll do, we'll switch it to the sine wave first of all, and set the output gain control potentiometer there to maximum, and I'm just going to trim the preset so we have, in fact it's just more or less there actually, but that's basically trimming the preset there to give us a 6 volt peak to peak sine wave signal coming out, which is there, and then switch to square wave, and we will try and adjust the preset there to get also 6 volts peak to peak. At the moment we've only got just less than 4 volts, so if I try and adjust the other preset, and what I'm finding here is I'm not able to alter the amplitude very much of that, and I suspect it's due to the DC level voltage input from the square wave going into the op amp there. So what I'm going to do is I'm going to isolate that from the previous stage by using a small capacitor. I'll try a 0.22 microfarad. So let's see if that works. So there we go. So what I've done now is I've simply connected a 0.22 microcapacitor on the input side of the positive input connection of the op amp for the square wave, and now let's see if we can adjust the amplitude of that for 6 volts. Yes, there we are. So there we have 6 volt peak to peak. So if I switch between sine wave and square wave, it should be the same. There we are. So we need to have a little isolating capacitor coupling the square wave signal to the operational amplifier, and that's then allowing us to control the gain of the stage to give us our 6 volt peak to peak. Now the gain control we can simply use to set the output level, and it should be the same for both the square wave or the sine wave. Then we can flick it onto triangular wave, go back to square wave, flick the switch over to give us the pulse, so we can alter the pulse width of the signal there. Back to normal square wave, flick it back to sine. So that seems to be working fine there now. Just to quickly show you where we put the capacitor to solve that little problem, I put a capacitor in there. I used a 0.22 microfarad, although it's not too critical, and that then allowed us to trim the gain there correctly. Here you can see I have the frequency set by having 2 capacitors there in parallel for the moment, so that's setting now the lower frequency range. So let's just see what the range of that is. So if I take the controls to the minimum frequency, so there we're getting a frequency of around about 87 Hertz at the moment. If we take it now to the, if we increase the, sorry, I'm getting down to, well, 72, 71 Hertz is the lowest frequency. So if we now increase the frequency to a maximum on that range, and we're getting a maximum frequency there of 6021 Hertz, that's 6 kilohertz. Now if I remove the larger of the value of the 2 capacitors there, leaving the smaller value in, it'll go to the next frequency range, and that's given me now maximum frequency there of 64,983 Hertz, so that's 64.9 kilohertz. And you'll notice now that we've got past the issue that we had previously, where we could only get to just over 32,000 kilohertz, and that was solved thanks to some very good suggestions from some of the viewers, and I altered the software for the Arduino. I incorrectly set the data as an integer for the frequency, and that was restricting the range, so I changed that, and now I can get frequencies going much higher. In fact, I can go to in the hundreds of kilohertz if I were to change the capacitor to a much smaller value capacitor. Now the new software version for this project I'll put in the comments below, and you can download the latest version of software that solved the issue we had with the previous version. So if we take this now to its lowest frequency with this capacitor in circuit, and we're getting around, well, 783 Hertz. So it's going from 783 Hertz all the way up to 64.9 kilohertz. Now you'll notice that we have a slight delay on the frequency indication there, and that's due to the timing, the gating signal that I've used in the software. I have a 1 second I think signal to monitor the frequency. We could play around with that, see if we could improve that, but this seems to work reliably, and you just get a little bit of delay from having set in the frequency to the display giving you the frequency indication there. Let's have a look at how we're going to house this project and build it into a project box. So that's the next thing we'll do. Well, to house this project today, I was looking around and I came across this nice little project box which I found on eBay. It has a clear red transparent front panel, which would be quite nice for our display to go behind, both on the front and the rear of the project box. So this one is quite nice. The height of it is around 60 millimeter, which is quite nice for our project. Maybe a little bit tight, but let's see how we can lay out our project within this project box. Here we have a closer look at the project box. The lid just simply comes off, and it also comes with some little rubber feet and the fix-in screws for screwing the top to the bottom of the case. Both the front and the rear panels are removable, which is quite nice, so that will make it easy for us to mark and drill these panels to fit our controls and switches on. And the other nice point is that you've got some fixing points here for fixing down your either PCB or your matrix board. As this is a one-off project, I think what we'll do today is we'll use a little matrix board to build the project on. We may at a later date then design a PCB. Let's now have a look at the other components and how I'm going to try and arrange the setup of this in this housing. This is the matrix board that I plan to use today to build the project. I just need to cut it down to size so it fits in the project box, and then drill some holes so we can fix it onto the fixing points in the bottom of the project box. And the other thing I was considering is how am I going to fix the display, and I want the display to sit behind the front panel so it shines through, but obviously I need to near the top, and it needs to be seated much higher than the base of the project board, so I need to suspend it somehow. And what I've decided to do is use some of these spacers, these hexagonal spacers. I probably need to use 2 of them so I can screw 2 into each other, and then my idea is these will then bolt through onto the matrix board, and then if I cut a slot into the top of these so I can slot them onto the display, then we can support it on the project board. I'll show you that when I do it. I'll just cut the board down to size, and then I'll lay some of the main components on there just to give you some idea how we can place the components for the project. So let me do that and we'll come back and have a look at that. Right, well I've cut the matrix board down to size, which is probably around about the right size. I've got some holes I just made there for fixing it into the base of the project box, and then I've just quickly laid out some of the positionings that I'm considering using for the component layout. So I've got the Arduino Nano there on the bottom corner of the board, and then the IC holders here. One will be there for the oscillator IC, the function oscillator IC. This one here will be for the Schmitt trigger. These two small ones, the 8-pin dowels, are for the dual op amps in the output stage. And then I've just temporarily positioned the some of the potentiometers here at the front. I'll have the frequency adjustment there, so I'll have the coarse and the fine frequency adjustment. I thought I might use a push button there to switch between sine wave and triangular wave, and this control here, I think I'll use that as the gain control, and the switch there, I think I'll use a switch, a simple switch, to switch between square wave or sine wave output, switching the output. Now what you also see here is I did make these spacers and just fix them onto the matrix board and put some cut some slots in the top, and the idea now is that the display should now just simply sit on that. So let me just show you that. Presses it in. I'll just turn it round and you can see, get the idea. So you can see now that I've spaced and positioned the display now so it sits above all the controls, and it's held in place by the spacer there, which is bolted down onto the matrix board. And probably what I will do when I've positioned it all in place, finally I'll probably put a little blob of silicone or glue or something just to make sure that the display is fixed permanently in that position. So there's a closer look there of the front of the matrix board with the controls and switches fitted and the display positioned above. The output socket, I'll use a BNC socket which I'll fix onto the front panel. But what I'll do with the controls, I'll drill holes in the front panel so these will then slot through. So let me just quickly do that, and we'll come back and have a look at that. I've now I marked and I drilled the holes here for the controls and the switches to come through, and as you see, the final hole that I made, I've bolted a BNC socket which will be the output. Now because I have a limited amount of space here, I'm going to probably have to put some of the other switches and controls on the reverse of the project box, and I'm thinking there particularly of the pulse switching part of the circuit. So let me just position that over the controls and you'll see how that looks. Right, well now you can see the front panel now slots on quite nicely, and you can see how the display is very nicely positioned on the reverse side of the front panel. And because the controls here are quite close together, I'm going to use some small control knobs, and I found these little push-on knobs which I'm going to use on all the controls on the front panel. So basically the first two there will control the frequency, this one will control the gain, the push button switch will switch between sine wave and triangular waveform, and the little switch there at the end will switch between the square wave and the sine wave. The Arduino Nano here, you see, what I'm doing, I'm going to have that plugged in, and I'm using these strip connectors here which I'm going to position on the matrix board and then the Arduino Nano will simply then just plug into that. So it'll make it easier to plug in or remove from the board. Well, I was just looking at ways of if I'm going to use this little switch mode 12 volt power supply here, of whether that could be housed in the box, and it just about fits. There's different versions of this type of switch mode power supply that you can buy on eBay. This is just one of many. But if you didn't want to use this, you could go back to the original idea I had on part 1 of the project. But what I might do here today is try and build this into the project box, and to do that I've had to just rethink the layout of the other components on the matrix board. So what I've done here, you can see I'm considering now putting the function generator IC probably around there, the Schmitt trigger IC there, and then the 2 op amps for the output stage there, which is near the output BNC socket on the front panel. And then I thought it might be a good idea to have the Arduino positioned somewhere around here, which would mean that I could put a little cutout in the side of the project box, which will allow us to connect the little mini USB socket for programming purposes from outside, so we can program it once the whole project is put together. So let me go away. What I'll do now is I'll cut the matrix board down to size so I can fit the switch mode power supply on in the project box, and I'll fix some of these permanently onto the matrix board, and then put some of the wiring in and position some of the little little presets, and then we'll come back and have a look. Well, here you can see now the board with all the components fitted and wired up. If we have a closer look, you'll see that I managed to get all the components neatly on the matrix board, quite compact. The switch at the side there is to simply switch the frequency range, the 2 capacitors there, and I think what I'll do is drill another hole on the front panel and put that switch just above the output socket. The display module, as you can see, is positioned there above the controls. I'll just give you a closer look at the board itself, so you can see how I've finally laid out the components and the ICs. I made 1 or 2 changes from my previous thoughts. Right, well, here you can see a better look at the matrix board itself with the layout. I'll just quickly identify the components on the board. Down there you can see I've put the 5 volt regulator IC with its associated capacitor, and I put a small heatsink on that. I'm using a 1 amp 5 volt regulator there. The Arduino is socketed and sits just on the edge of the board and overhangs slightly to give us access from the slot in the casing. The chip there, that's the main function generator IC, the XR2206, and the associated presets there for setting the symmetry and the sine wave shape. The push button switch, you can just see there, that's switching between triangular waveform and sine waveform output, and then just next to that you have 2 more presets, and they set the initial amplitude of the triangular waveform and the sine waveform to balance the 2 out. There you have the 74HC14, the Schmitt trigger IC there. There's several Schmitt triggers in there. At the moment I'm using 2 of them, but I'll probably use a 3rd one to give us a TTL output as well on the back of the project box. And then in this corner here you can clearly see we've got the 2 operational amplifiers. They're dual packages, so in total we have 4 op amps, 2 in each, and the associated presets there that set the gain of the sine wave stroke triangular wave and the square wave output. So we balance the output of the 2 so they match. Here we can see we have the display module, which is seated in those spaces that I mentioned earlier. what I'll do, I'll just remove that, and you can see the controls underneath it. The green and orange wires you can see there are feeding the little switch and the two capacitors there. That switch in the two capacitors, depending on the frequency range you wanted. Remember, we had a 0.022 microfarad and a 0.22 microfarad, so we can switch between two frequency ranges. Of course, you could replace this with a rotary switch and have several different value capacitors there to give you a much wider range than what I'm doing here today. Anyway, there's the board. I've just hardwired it underneath. I may at a later stage design a PCB for this, but for the moment, as it is a one-off, it's on a matrix board, and I'll just quickly show you the underside. It's all hardwired underneath, so I've just wired it across. I actually have positioned one of the resistors as well on the bottom of the board, just for convenience really. Okay, well there we are. So what we'll do now is I'll put the display back on the spacing fixings there, and we'll just test and see if it's working correctly. Well, here you can see now I have the little project board there connected up to the 12 volt switch mode power supply module I have here, which I'll be using, and the 12 volt DC is going into the board, and then the additional 5 volt regulator on the board to feed the Arduino and the display and the logic ICs. So what we'll do now is I'll switch on and monitor the output on the oscilloscope and the frequency reading on the digital display. So there it's set, comes up with Scullcom to start with, the display there resets, and finally gives you a reading of, in this case, 7,698 Hertz, which corresponds quite nicely to the oscilloscope showing 7,703, so fairly close to what we're seeing on the oscilloscope. And you can actually trim the accuracy of the display here in software on the Arduino software. So we're on sine wave output at the moment. I'll just demonstrate the gain control for the output. So you can see there we can control the gain of the output, and we can switch between sine wave and triangular wave by the push button, or we can switch the output by the little toggle switch there to square wave output. So that all seems to be working fine. The two controls here, as I say, the frequency control, the coarse adjust and the fine adjust, so we can alter the frequency and we can adjust the fine adjust of the frequency there. It gives you a little bit more control over the frequency range, and what you'll notice is there's a slight delay on the digital display here catching up with the actual frequency reading, and that's a function of the software at the moment, which we may have a look at that and see whether we can improve that in software. But it all seems to be working fine. As you can see on the oscilloscope, we have a little bit of overshoot there on the square wave on the leading edge. I'll just expand the ring on this, and you can see that that slight overshoot. We could probably get rid of that by adding a small value capacitor in the feedback loop on the operational amplifier in the output stage there. So I'll come back to that and we can see whether we can improve on that. But really that's quite a minor issue. Just go back and have a look at the sine wave, looks fine. So everything appears to be working fine, and we have no issues at all. The switch there, as I say, we can switch the frequency range. So switch to a lower range. Let's just see what we have now. we can go right down. We can go right down to nearly 41 hertz there, so a low frequency, and increase that up on that range, goes up to 935 hertz after the fine adjust. So on that particular switch range it goes from about 41 hertz all the way up to 3938 hertz. If I switch the range, the highest it's going up to there, as you can see, is 45,577 hertz, and that range will go down that range goes down to just slightly over 404 hertz. So I think you've got two very broadband ranges with that switch, just simply with two capacitors. So what we'll do now is we'll have a look at fixing this board in the project box with the front panel, and look at how we're going to position the frequency range switch. Right, well here you can see now I've got everything boxed up. The board is firmly fixed in the base of the board, front panel on, the 12 volt switch mode power supply is bolted onto the bottom of the casing using plastic spacers to make sure it's safe and isolated, and then I'll probably take the mains cable out through a rubber grommet on the back panel. You could even add a on-off switch if you wanted on the rear of the box. Now the other options that we have with this, if you remember, is we have a pulse mode option, and there wasn't sufficient space on the front panel to put the control and the switch for that, but that could be fitted on the rear of the panel here, the rear panel, and you could also add on the rear a TTL output, square wave TTL output, with a second BNC socket on the back. And for those that were wanting to use this also as a standalone sort of frequency counter, we can add another switch if you wanted to switch the function of the internal frequency counter to use as an external frequency counter with the BNC socket. So I think what we'll do next is we'll just switch on and have a look, make sure it's working correctly. Okay, let's just switch on, make sure everything's still working. Okay, it goes through the startup sequence, and it's displaying at the moment 13,240 Hertz, 13.2 kilohertz. So if we connect the BNC now on the front panel to the oscilloscope, and we're getting sine wave out. Let's just press the button and see if we get triangular waveform. Yep. Switch there for square wave. Yeah. And then the switch there is the frequency range. That seems to be working fine. I'll just quickly show you how to set these two presets here, which are in the output stage of the op amps. Basically what you do, quite simply, set the function generator initially for a sine wave output, turn the gain control potentiometer fully clockwise for maximum outputs, and note the reading. And what we're looking for here is a reading of around 6 volts peak to peak. That's slightly low there, so we can just adjust the little preset there, and as you see we're getting, there we are. So there we now have a sine wave signal on the output at 6 volts peak to peak. Then flick the front switch to square wave and adjust the other little preset there on the op amp to also give us 6 volts peak to peak. There we are. So now when you switch between the two, the signal of the square wave and the sine wave are equal, and if we go to triangular wave, that's also okay. So the gain control now works correctly over the whole range on both the square wave and the sine wave. Well, I hope you found this project on the function generator of interest. The additional features, which is the pulse output and the TTL output, and also any other little modification I decide to do, I'll probably do that in a separate video. This has been quite a long one so far, so I'll leave it at that. But the function generator as it stands is quite a nice little addition to any workshop for the hobbyist, and I'll draw up the circuit diagram and put it in a link down below. I'll also give you the latest version of the software for the Arduino Nano, and that will be in a link down below as well. Well, thanks for watching, and if you found this useful, please give me a thumbs up, and I'll see you all again next time. Bye for now.